What if the fundamental algorithm that we've used to train every major vision language model for the last 3 years is actively forcing them to hallucinate?
Yeah, it is a huge problem that people are just starting to realize.
Right. Well, welcome to AI Paper Slop, where we break down the latest AI and tech research for you, the ML practitioners out there. We are jumping straight into a paper that fundamentally challenges the current multimodal pipeline.
It's called LeVLJEPA, which stands for End-to-End Vision Language Pre-Training Without Negatives by Lucas Kuhn and team.
And for anyone building vision language models right now, here is the core insight you need to know up front. The dominant architectures like CLI, SigLIP, basically anything relying on contrastive learning, they demand massive batch sizes to generate negative samples.
Right. Tens of thousands of samples per batch.
Exactly. And they primarily optimize a single pooled image embedding. But LeVLJEPA throws all of that out. No negative samples, no temperature parameters to tune.
No momentum encoders either.
Right. Instead, it relies entirely on cross-modal prediction using stop gradient targets, combined with a distributional regularizer called SIGReg to prevent the representations from collapsing.
Which is really the secret sauce of the whole thing.
Yeah. So the bottom line for your deployment pipeline is this. While LeVLJEPA matches CLIP on standard linear probing, it absolutely crushes contrastive methods on dense semantic features.
That's not even close.
Right. So if you are using a frozen vision backbone to feed patch tokens into an LLM right now, this paper proves you might be using the wrong visual encoder.
The contrastive bottleneck is very real, and the field has, frankly, been optimizing for an outdated metric for a while now.
Yeah, let's trace that shift in the architecture pipeline. Because the way you guys deploy vision encoders today has completely transformed compared to when CLIP was first introduced.
Exactly. The pre-training objective just hasn't evolved to match those new deployment realities. 3 years ago, a vision encoder was primarily evaluated as a zero-shot classifier.
Right, you would just run an image through a vision transformer and pull out the global CLS token.
Yeah, that single 768-dimensional vector that's supposed to summarize the entire image. And then you check its cosine similarity against a text embedding.
But the models you're all deploying today, things like ALAVA, dense CLIP,
or even robotic control architectures like CLI port.
Right, those do not consume a single pooled vector. They take the full grid.
They require the model to attend over the full grid of patch tokens. If you pass an image through of EVEB16, the downstream language model is looking at 196 distinct patch tokens.
And the spatial relationship and those granular semantic details, I mean, that is the actual payload.
Precisely. The language model needs to differentiate the object in the top left corner from the background in the bottom right. But contrastive vision language objectives, by their very mathematical nature, are primarily optimizing that single pooled CLS embedding.
Just to align globally with a sentence.
Right. So they only supervise the rich per token features as this sort of secondary byproduct of that global push and pull.
I always think of contrastive influency loss as like a speed dating algorithm.
Oh, that's a good way to put it.
Yeah, it scans a massive batch of images and captions, finds the matched pair, and pushes them together in the latent space, and then it violently pushes all the unmatched pairs apart.
Right. It is highly effective at that global room-level sorting.
But it doesn't care about the deep personality traits, right? The dense, localized, token-level features, not unless those features happen to help with that initial superficial match.
Exactly. And the strange part is, in the vision-only self-supervised learning world, we moved past this years ago.
Yes. We transitioned to non-contrastive methods like DNO and JEPA, so why hasn't vision language caught up? I mean, why couldn't we just port those non-contrastive methods directly over to cross-modal data?
Well, adapting non-contrastive methods to cross-modal data introduces a really unique, basically catastrophic risk of representation collapse.
How so?
Think about vision-only learning with a model like JEPA. You are taking two augmented views of the exact same image and mapping them together. The structural information is completely symmetric. But cross-modal data is fundamentally asymmetric. You are trying to map a highly dense, information-rich image space to a relatively sparse, coarse text caption.
Ah, okay.
So when you try to adapt a non-contrastive prediction method to this cross-modal setting, the optimization process naturally takes the path of least mathematical resistance to minimize the loss.
Which basically means the architecture just collapses into whatever minimal coarse information the image and text happen to share.
Exactly, discarding all the dense visual details we actually care about.
Wow. Okay, so to see how the LeVLJEPA architecture solves this, we need to look at their baseline setup They use a standard vision transformer for the images.
Right. And a standard GPT-2 model for the text.
But instead of pulling those embeddings together globally with a contrastive loss function, they use cross-modal prediction.
Yeah, they set up standard MLPs where the image embedding is explicitly forced to predict the text embedding, and the text embedding predicts the image.
But there's a huge trap here, right? Because the paper includes this fascinating ablation study on this exact setup.
Yeah, the collapse problem. If you implement a direct symmetric mean squared error loss.
Wait, meaning you penalize the difference between the image prediction and the text target and vice versa.
Right, and you allow the gradients to flow freely through both the image and text networks. If you do that, the representations completely die.
Oh, wow.
The effective rank of the embeddings drops to just 3 on the vision side.
That is crazy. A rank of 3 in a 768-dimensional space is, that's a total loss of variance.
Complete loss. The objective forces both the image encoder and the text encoder to abandon all their rich, distinct features.
Just to meet in the middle.
Exactly. They crush themselves into a shared, highly compressed, low-dimensional subspace because that is the easiest way to minimize the symmetric MSE loss.
So they only retain the absolute most primitive overlap between the image and the text, like maybe basic brightness or a primary color.
Yeah, and they just ignore the other 765 dimensions of potential variance.
Imagine two people trying to find each other in an incredibly dense fog. That's our symmetric loss landscape. One person is the image representation, the other is the text.
Okay, I like this analogy.
Because they are both moving toward each other simultaneously based on the MSE gradient, they will eventually meet in the middle. But they will have completely lost their original geographic coordinates.
Right. They abandon their grounded features just to close the distance.
Exactly. So the authors introduce a 2-part fix for this, starting with stop gradients. To fix the fog problem, you basically freeze one person.
You designate the target as a grounded landmark that cannot move.
Right. And the predictor has to navigate the entire way to them. So in practice, the gradients only flow through the predictor network and its own encoder, never into the target encoder.
And that stop gradient creates a critical asymmetry in the optimization landscape. It ensures the image encoder is shaped strictly by its own prediction task and its own regularization.
So it prevents the text encoder from dragging the image representations down into that compromised, low-rank middle ground.
Exactly. However, stop gradients alone aren't enough to prevent the embeddings from degenerating or sort of shrinking over a long pre-training run.
Right, you need a way to force the embeddings to actually utilize the entire high-dimensional space.
Which requires the second component, SIGReg, or sketched isotropic Gaussian regularization.
Which is quite a mouthful. But SIGReg basically operates independently on both the image and text modalities to keep their marginal distributions as close to an isotropic Gaussian as possible.
Right, and an isotropic Gaussian is the mathematical ideal here because it ensures the embeddings are spread out uniformly across all available dimensions.
It maximizes the informational capacity of the latent space.
Exactly. It directly counteracts that rank collapse we saw in the ablation study.
But doing density matching in a 768-dimensional space usually triggers the curse of dimensionality, doesn't it? Like scaling the compute requirements exponentially.
Yeah, trying to directly measure and enforce a multivariate Gaussian distribution in high dimensions is totally computationally intractable for tree training.
So how does SIGReg bypass this?
Through a clever application of statistical theory. Rather than evaluating the full high-dimensional space, it randomly projects the embeddings onto a set of 1D directions.
Just simple univariate lines.
Exactly. Then it applies the Epps-Pulley normality test to each of those 1D projections.
Okay, the Epps-Pulley test uses empirical characteristic functions, right?
Yes. It compares the Fourier transform of the empirical distribution against the theoretical characteristic function of a normal distribution.
Wow, okay.
It is mathematically grounded in this principle that if all 1D projections of a multivariate distribution are Gaussian, the joint high-dimensional distribution must also be a multivariate Gaussian.
So by running this characteristic function-based test on random 1D lines, SIGReg enforces the isotropic Gaussian penalty in linear time and linear memory.
Yes. It forces the network to maintain full-rank, highly expressive features without the computational nightmare of high-dimensional density estimation.
Okay, so we now have a theoretical model that uses cross-modal predictors, stop gradients acting as our grounded landmarks, and SIGReg keeping our distributions perfectly isotropic.
That basically solves the architecture.
But translating this to real-world ML engineering introduces the whole problem of training constraints, because contrastive methods like CLIP are notoriously brutal on compute infrastructure.
Oh, they are. because they rely on the denominator of the info and CE loss function.
Right. To get good, hard negative mining like the difficult examples that force the model to learn fine-grained details, you need batch sizes in the tens of thousands.
And most research labs simply do not have the GPU clusters to support a batch size of 32,000.
No, it's insanely expensive. And if you shrink the batch size for a contrastive model,
The performance degrades linearly. You only end up with easy negatives in the batch.
like comparing a dog to a car.
Right, so the model never learns to differentiate nuanced features. But
Well,
LeVLJEPA is mathematically indifferent to batch size.
because the cross-modal prediction is calculated on a per-sample basis.
Exactly. And SIGReg acts on the empirical marginal distribution. So the optimization converges to the exact same population objective, whether your hardware limits you to a batch size of 1024, 2048, or 4096.
That completely democratizes the training compute required to build frontier vision language models.
It really does.
The compute advantage is clear, but we have to look at the empirical benchmarks here. The authors train LeVLJEPA on the CC12M dataset and the 92 million sample DataComp-L dataset.
Right.
And when we look at standard linear probing, where you freeze the CLS token and train a basic linear classifier on top of it to test how separable the classes are, LeVLJEPA operates basically on par with InfoC and SigLIP on datasets like ImageNet, Places 365, and Aircraft.
Which shows the global visual feature is highly discriminative.
But I do have to push back a little on the DataComp-L scale results, because the paper openly shows LeVLJEPA trailing CLIP and SigLIP on zero-shot alignment.
He does.
On zero-shot ImageNet, SigLIP hits roughly 50% accuracy, while LeVLJEPA sits down around 42%. That is an 8-point gap for an architecture claiming superiority.
Well, you have to isolate what zero-shot classification is actually mechanically measuring.
Okay, lay it out for me.
In a zero-shot evaluation, you embed an image, you embed multiple text prompts, like a photo of a dog versus a photo of a car, and you measure which pair yields the highest cosine similarity.
Right.
That is a direct test of matching a true pair while rejecting a negative pair. That is the explicit discriminative objective that the info and CE loss function optimizes for during every single step of contrastive pre-training.
Oh, so contrastive learning is literally training for the zero-shot test.
It is the exact same mathematical operation. LeVLJEPA, by design, never sees a negative pair during training. It only learns through matched pair prediction.
So it hasn't been explicitly optimized to push away close negative captions in that specific cosine similarity format?
Exactly. The 8-point gap on zero-shot ImageNet isn't a failure of the visual feature's quality. It is a structural alignment gap. The linear probing parity proves the underlying visual features are just as strong, they just aren't indexed for direct cosine discrimination.
That makes a lot of sense. And we also see LeVLJEPA's global features outperforming contrastive models in background robustness, right? Specifically on the ImageNet 9 challenge.
Yeah, that test is really revealing.
So for the listeners, you train a linear classifier on images with their original backgrounds, and then evaluate it on images where the backgrounds are artificially swapped.
Right, they test mixed same, where the background belongs to the same class.
And mixed rand, where the background is swapped with a totally random class, like putting a dog in a submarine environment.
Yeah. And contrastive models frequently rely on contextual shortcuts. If CLE sees blue water, it might classify the object as a boat purely based on the background vibe, completely ignoring the primary object.
So under the mixed rand shift, info and C models suffered massive accuracy drops, like almost 19 points.
The LeVLJEPA suffered the smallest accuracy drop across the board, dropping only about 17 points.
Because the non-contrastive global features are fundamentally more object-centric. The prediction objective forces the model to reconstruct the actual semantic latent representation of the subject, rather than just finding a lazy global shortcut to satisfy a contrastive match.
Precisely.
So let's shift from the global pooled embeddings to the dense patch-level tokens. Because the fundamental thesis of LeVLJEPA is that discarding contrastive negatives produces vastly superior dense features for those 196 patches.
Right, and they test this through semantic segmentation on 80, 20K, and COCO stuff.
They take the frozen patch tokens from the VIT, locking the encoder so there's absolutely no fine-tuning, and simply train a single linear layer on top to predict the semantic class at every spatial location.
And LeVLJEPA beats the strongest contrastive baseline by over 2 MIOU points on both datasets.
Wow.
When the task head is restricted to a single linear layer, you cannot attribute performance gains to the capacity of the task head.
So a 2-point gap on a frozen linear probe confirms that the spatial and semantic structure natively embedded in LeVLJEPA's patches is explicitly better out of the box.
Exactly. Contrastive models neglect per-token structure because the loss function only scores the pooled summary.
But by predicting rich latent targets, LeVLJEPA preserves high-fidelity, localized semantic data in every individual patch.
Which brings us to the ultimate deployment test for ML practitioners, using the vision encoder as the frozen visual front end for a large language model.
Yes. The experimental setup here is super rigorous. The authors take the frozen VIT-B16, a completely frozen LLM, and only train a light-rate MLP bridge to map the visual patch tokens into the language model's embedding space.
So if the resulting VLM performs well, it is strictly because the visual tokens provided superior structured information to the LLM.
And they ran this suite with 2 different LLMs, Llama 1B and Qwen 1.5B, just to rule out tokenizer artifacts.
And the results show total domination by LeVLJEPA across the board.
I mean, look at GQA, which tests localized compositional reasoning. It asks questions like, is the red block to the left of the blue cylinder?
Which requires really precise spatial grounding. And LeVLJEPA beat Info and Ease by almost 2 points with Llama and 1.5 points with Qwen.
And on VQA V2, which evaluates general visual question answering, LeVLJEPA scored nearly 5 points higher than the strongest contrastive baseline when paired with Qwen.
But the POP benchmark results reviewed the most critical flaw in contrastive models.
Right. POP-A tests object hallucination by asking balanced yes or no questions about whether a specific object is present in an image.
And contractive backbones exhibit a severe yes response bias. They artificially inflate their recall metrics by constantly hallucinating objects that aren't actually in the scene.
Why does that happen?
Well, it happens because of how contrastive loss clusters concepts. It pulls the text embedding for bicycle and the global image embedding for a street scene closer together during pre-training.
Even if the bicycle is just a contextual association rather than a physical object in the pixels.
Exactly. So when the LLM receives those globalized, context-heavy patch tokens, the latent space is already biased toward the concept of a bicycle. The LLM reads that semantic signal and outputs yes, hallucinating the object.
Oh, wow. But LeVLJEPA avoids this entirely, producing the most balanced and calibrated answers on the POP benchmark. Its yes rate hovered incredibly close to the ideal 50% mark.
Because its dense tokens are trained via localized prediction rather than global pulling. If the pixels representing the bicycle aren't there, the feature simply isn't present in the latent space.
So the language model receives grounded reality, not contextual bias.
Right. The fact that LeVLJEPA was the worst at zero-shot alignment but the absolute best as a VLM backbone shatters the long-held assumption that a good zero-shot classifier makes a good visual feature encoder.
It really forces us to reevaluate our selection criteria for multimodal architectures. If you optimize for cosine similarity on ImageNet, you are actively selecting for an encoder that will degrade the spatial reasoning and factual calibration of your downstream language model.
That's exactly the takeaway.
So, if you are an ML engineer building dense prediction systems or training the next generation of visual instruction-tuned models, non-contrastive pre-training is the required path forward.
Yeah, LeVLJEPA proves you can achieve rich, spatially aware token representations without relying on massive batch sizes.
It provides superior robustness to background shifts, and it gives your LLM the exact localized grounding it needs to stop hallucinating objects.
And, the architecture also points toward a much larger paradigm shift.
Oh, how so?
Consider the mathematical output of SIGReg. It explicitly enforces an isotropic Gaussian distribution for all the visual embeddings.
Right.
So these visual features exist in a uniform, continuous, normally distributed latent space. But in the current pipeline, we use an MLP bridge to clumsily map those continuous visual features into the discrete, tokenized embedding spaces of LLMs.
Basically forcing a translation between 2 entirely different mathematical languages.
Exactly.
I mean, we are still trying to make continuous visual reality look like discrete text tokens just so the transformer can digest it.
Right, so what happens when we stop forcing that translation?
That's a huge question.
If we natively pre-train our future language models to directly ingest these continuous, normally distributed visual features from day one, we might eliminate the multimodal hallucination gap entirely.
Wow. natively multimodal LLMs that don't just bridge to vision, but speak its exact statistical language from the ground up.
Something to consider testing in your next architecture run.
Absolutely. Well, that wraps up this breakdown of LeVLJEPA on AI paper slop. Thanks for joining us, and we will catch you in the next deep dive into the research.